Okay, good morning. Let's begin. Last lecture of the course, today we'll cover applications of multi-rate signal processing, and let me begin with a quick review of what we had covered in the last lecture. We're trying to look at quantization and whether any multi-rate techniques could help us in the aspects of quantization. The conventional way is that you sample at or just above Nyquist, quantize the signals based on the number of bits of precision that you want, and then apply the coding scheme and then give out a value that is proportional to the quantized value. So, this particular model gives us a way of characterizing the quantization noise, and that would be as an additive impairment. So, you think of quantization as a additive process where you add a error term or a noise term that gets added, that gives you a perturbation of the unquantized signal. Now, yesterday we went through the lecture and we showed that when you have a b plus 1 bit representation, b plus 1 bit 2's complement representation, that is one of the standard forms that is used, and we derived the signal to quantization noise ratio representation. Okay, so the SQNR can be expressed in the following way. It was 6.02b plus 10.8 minus 20 logarithm base 10 of the ratio of the maximum or full scale divided by the standard deviation of the input signal. Okay. So, one observation is that this is a design choice. You have to choose how much you want to choose your full scale, design choice, and the design choice is controlled by your desire to minimize the probability of clipping. So, you want to minimize the probability of clipping. The reason is probability the clipping gives you a very nonlinear distortion, a very severe form of distortion, probability of clipping. You want to capture most of your signals within the range that for which you have designed your A to D. Now, clipping is nonlinear. Is quantization nonlinear as well? Quantization nonlinear as well? You quantize A, you get a certain value, you quantize B, you get a certain value, add them together and you quantize, you will get something totally different. So, it is not linear. So, quantization itself is a nonlinear operation. So, quantization is to begin with nonlinear, but we have come up with a linearized model where we said it is going to be in the range of operation, in the what we call as the nominal operating range. That means you are not in the clipping zone. We have made it into an additive impairment. So, basically it is something that we can analyze. There are the properties of linearity, superposition, all of those would hold. So, in the nominal operating range, we have modeled it as a additive impairment. Okay. So, we modeled it like a noise like impairment, and which is very advantageous because in communications this is something we do all the time, and we have several tools by which we can assess the impact of these impairments. Okay. So, this is the broad framework that we have worked with. I thought I could write down equation or just do one example just to strengthen what we had already done. Okay. Example for the, so supposing you are told that you have a 12 bit A to D uniform 2's complement, okay, uniform quantization, rounding using 2's complement, okay, comma 2's complement. What is the expected SNR, SQNR? Okay. First thing to keep in mind is that B plus 1 equal to 12. Okay. The number of bits totally available to you is equal to 12, implies B for all the formulae has to be B equal to 11. So, the approximate SQNR from our expression will be 6.02 into 11 minus 1.25. If I have chosen the, this is assuming that we have chosen the full scale as by sigma x equal to 4, then you get this 1.25. If not, you would have to recalculate that. So, this comes out to be about 64.97 dB. We can say that it is about 65 dB. Okay, that is what you will get with a 12-bit quantizer with 2's complement, uniform step levels. And so, to add to this, we said that you could okay, just make sure you are okay with this 65 dB, that is roughly the range that you will get. Okay. Now, look at the oversampling element. Oversampling element says I am going to do oversampling by a factor of m at the input. So, the quantization will happen like before. Basically, the quantization noise gets spread out, and then we use a low pass filter with the appropriate downsampling to get back to the Nyquist rate or as close to Nyquist rate. And we said that there is a advantage that we can get with the oversampling rate, and that oversampling rate based expression yesterday we derived. Let me just write that down for you so that we can build on this equation. So, in this particular case, the quantization noise expected value of x dE of n whole squared comes out to be 1 by 12th of the original expression. Delta squared by m was the original expression, and because of the delta squared by 12 was the original expression, and 1 over m is the modified expression. Okay, so 1 over m is the new advantage or the new factor that we have brought in. So, effectively this is equal to 1 over 12 m x m by 2 power b whole squared, which you can rewrite the equations. Yesterday we did a expression in terms of log base 10. I am going to do it slightly differently so that you just sort of get a different perspective. I am going to take logarithm base 2 for this expression. So, 2 power 2b is equal to, so basically rewrite this, it is 1 over 12 m x m squared divided by, if I call this the power of the signal dE. Okay, so, this is divided by p dE. Okay, this is a new equivalent representation of the previous expression. Now, taking log base 2, logarithm base 2, I get 2b equal to minus 1 by minus log base 2 of 12, log base 2 of 12 minus log base 2 of m minus 1 minus log base 2 of p dE plus 2 times logarithm base 2 of x of m. Okay. And I am going to take the b across to the other side just for minus 1/2 log base 2 of 12 minus 1/2 log base 2 of m minus 1/2 log base 2 of p dE plus the 1/2 and 2 will cancel, log base 2 of x of m. Okay. Now, I am going to put a tick mark on those things that are constants. Okay. That is a constant, this is a constant, this is a constant. So, basically I want to relate b and m. Okay. Now, given this scenario, the relationship between B and M says B is equal to 1/2 log M minus 1/2 log M. So, if I set M equal to 2, log base 2 will be equal to 1, B will be equal to the new value of B will be B is equal to B old minus 1/2, correct. Whatever was the rest expression, we call it as B old, then minus 1/2. Okay. So, this is what we said yesterday, that doubling of the frequency translates into a reduction of 1/2 bit. So, B is the number of bits of precision that you need to achieve a particular error variance, and if you have M equal to 1, you go back to the original equation. Now, if you have the new with the oversampling, it becomes, so similarly you can substitute and you can find out what is the corresponding level. So, M equal to 4, basically you will get B old minus 1, okay, and every multiple of 4 subsequently you will get an additional reduction of 1 bit. Okay. So, again what we are trying to work towards is, so if I ask you to tell me what would you get if M was equal to 256, of course you can plug in and do it, but you can write it as 4 times 4 times 4 times 4, 4 to the power of 4. Each of these would contribute 1 bit. This is 1 bit, 1 bit, 1 bit, 1 bit. Add all of these together with the overall minus sign. So, B will be equal to B old minus 4 bits. You have reduced your precision requirements by 4 because you have increased your oversampling by a factor of 256. Okay. Now, it turns out that this is good. It is good to know that multirate can give you a benefit. Of course, we want to ask the question, can we do a little bit more? So, that was where we ended the last class. So, we said that as long as the input error is white, this is the best that we can do. The only way that we could do is to color the input signal, and we said that this would be a way to do the coloration, and our goal today is to actually to derive this result and to build on that. Okay. So, the overall picture that we want to have is this block is very important for us in terms of our understanding. The lower block is the equivalent discrete time representation. So, this is a C to D block. You have we will assume that we would have done an oversampling by some factor. So, which means that at the other end we would this would not be the, we would have to do the downsampling, incorporate the downsampling. So, the downsampling will be a low pass filter with omega c equal to pi over m, whatever has been your oversampling at this point. So, if you have oversampled by a factor of Ts, oversampled by a factor Ts, then we would do the corresponding downsampling by a factor of m, and this is my output signal. Since it comes out of a downsampler, the notation used by Oppenheim and Schaefer, I have just used the same, is a combination of x d a for n. A stands for the input signal, the analog signal, that means it is a signal component. The other part is x d e of n, whatever is the error introduced by that. So, just an indication, this represents the signal component at the output, other one in the quantization noise component at the output. Okay. So, now an A to D converter, is it an analog device, is it a digital device, or is it a mixed signal device? What is the input is an analog signal, output is a discrete time signal. So, obviously, it has to be a mixed signal device. Okay. Now, where is the mixed signal boundary for us in this case? So, if you were to look at it as the input at this point where the analog is taken in, and then at the output the and the discrete time comes out, or if you were to take it in. So, essentially what we are doing is we are doing some modifications inside the mixed signal portion of it. Okay. We will do a discrete time equivalent and then say that okay, ultimately it is not just purely discrete time, it is going to be a mixed signal element. Okay. So, for the purposes of analysis we are using the lower block diagram, okay, and we will build on that. Okay. So, the task that I had given you was to obtain the transfer function between the input and the output. So, let us write down a general result which helps us uniformly, and so if I have the following setup where I have h of z as my forward transfer function and this is an additive node, input is x of n and I have a transfer function g on the lower branch which is the feedback branch, okay, and you would have seen this many times in the control discussion. There is a feed forward transfer function, feedback transfer function, and the output is y of n. Okay. So, the overall transfer function y of z divided by x of z is given by h of z divided by 1 plus g of z h of z. But for this minus sign, if the minus sign was not there, you will get 1 minus g of z h of z. Okay. So, this is the general form. So, now go back to this figure and do a transfer function between the input signal. Okay. Let this be the point at which we are interested in, x of n to the output y of n. Okay, we have not done the downsampling, we have not done the filtering post, basically just this portion of the transfer function. Okay, so what we will do is for the signal component, here's the signal component, please keep the diagram as your reference and verify that the forward transfer function h1 of z is given by 1 over 1 minus z inverse, and the feedback portion is given by g1 of z which is z inverse, okay, the feedback portion. So, the signal transfer function y of z divided by x of z is given by 1 over 1 minus z inverse divided by 1 plus 1 over 1 minus z inverse times z inverse, which gives us a transfer function which is equal to 1. Okay, that is the signal component. Now, move over to the noise component. Apply the same technique, obtain the forward transfer function h2 of z. In this case, notice that there is no other gain term, forward transfer function is 1, g of z, the feedback portion, it should be back to the point where the input signal entered the diagram. So, this will be equal to g2 of z which is z inverse divided by 1 minus z inverse, okay, and y of z divided by e of z, assuming there is no input x. I am just doing the analysis for this. This comes out to be 1 minus z inverse, you just apply that. Okay. Now, we are ready to invoke superposition. So, invoking superposition between the two linear inputs, one is x of n and the other one is e of n. So, the output must be the output due to each of those inputs. So, y of z, let me if I call this as h subscript x of z and this one as h subscript e of z. So, y of z is equal to h x of z times x of z plus h e of z times e of z, that comes out to be x of z plus 1 minus z inverse e of z. Okay. So, the input output between the whatever was the structure that we have implemented says that there is no the transfer function between the input x and the output is 1. So, there is no modification of the input signal, but the error signal got multiplied by 1 minus z inverse. So, what type of a filter is this? If you sketch this, 1 minus z inverse basically says that the 0 at omega equal to 0. So, it looks like a bowl. Okay. So, this is frequency, this is pi, this is 0 minus pi, this is magnitude h e of j omega magnitude. So, if I multiply my error signal has got a spectrum which is flat. Okay. If you multiply by this transfer function, the resultant now that is going to be showing up at my output is the original flat spectrum multiplied by a high pass spectrum, which means the energies in the low frequencies have been eliminated and the high frequencies components are still left there. Okay. So, the insight is that this type of a transfer function removes the low frequency noise components, low frequency portion of the quantization noise. Okay. Important to also highlight, the signal is lying in the low frequency portion. So, which means that effective signal to quantization noise ratio is now going to improve. Signal lies in the low frequency portion of the spectrum. So, the combination of these two says I am going to see a benefit in SQNR, benefit in SQNR. Okay. So, how much of a benefit and how will we leverage it, that is something we would like to quickly quantify. And so, is this okay what we have done? Basically analyzing the transfer functions, showing that the output is a input x of n plus transfer function times E of z. So, here is an equivalent diagram if you would like to draw it down, draw. So, the continuous time signal x a of t, which passes through a C to D converter oversampled. Okay. Let me just put a little note there that it is oversampled, and let me also indicate the oversampling factor as m. Then at this point it becomes a discrete time signal x of n oversampled. I need to add noise to it. Previously it was a white noise signal. We now have the white noise component still present, E of n, that is still the old assumptions, sample to sample uncorrelated, but it is passing through a filter 1 minus z inverse, which is going to introduce the coloration. So, this is where the coloration is going to occur. Okay. It also, coloration as I mentioned also means that there is sample to sample dependence, which is what is built in. Basically there is memory into the so we will call this as E hat of n, E hat of n. Now, these two get added together and it passes on, and then eventually will go through a low pass filter with cutoff omega c equal to pi over m, then downsample by a factor of m, and that will be our output x d of n. Okay, sort of a simplified diagram, but it is very helpful to visualize what is happening. Now, very quickly, what is the type of coloration that we have introduced? E of n is equal to E of n minus E of n minus 1, like a first order difference is what you are doing. Okay. So, if I were to write this as a filter h e of j omega, this will be equal to 1 minus e power minus j omega. Do a little bit of simplification, e power minus j omega by 2 what you will get within the bracket is 2j sin omega by 2. Okay. And we have a result which tells us that the spectrum of E hat, power spectrum E of j omega, will be equal to the power spectrum of the input signal E S subscript E of j omega times modulus of H E of j omega magnitude squared. So, when I pass white noise through a filter, the resultant power spectrum comes out to be the magnitude square of the filter, because the power spectrum of the. So, this is equal to sigma E squared modulus 4 times sin squared omega by 2. Basically, it is a magnitude square. Okay. So, now if I want to find out the total power, this is a power spectrum. So, if I wanted to find the total power at the output PDE, the general formula is 1 over 2 pi integral minus pi to pi the power spectrum of x E hat E of j omega d omega. Okay. But PDE is not measured here, it is measured at the output. At the output, what did we do? We already restricted it to pi over m. So, actually these limits are not correct. This should be minus pi over m to pi over m. Okay. So, please substitute for SEE, do the integration and verify that what comes out at this point is delta squared by pi sigma E squared is equal to delta squared by 12. So, that is where the delta squared is coming. So, delta squared pi squared divided by 36 m cubed. Okay. So, please do verify this result, just a very simple integral m cubed. Okay. So, maybe it is helpful for us to write it as delta squared by 12 delta squared by 12 into pi squared divided by 3 m cubed. Okay. Now, delta squared itself delta itself is equal to x of m subscript m by 2 raised to b. And now, if you write the log base 2 equation that we did in the beginning of this lecture, what you will get is 2b equal to 2 times logarithm logarithm based okay, log base 2 of 12 with a minus sign minus there is a pi squared by 3 minus there is a plus pi log base 2 of pi squared by 3. Just make sure I do not make a mistake in this equation, because yes, there is a plus log base 2 pi squared divided by 3, and of course the other two parts minus log base 2 of PDE and plus 2 times log base 2 of xm. Okay, I hope you can look at it and just verify. There is a minus 3 log base 2 of m, minus 3 log base 2 of m. Okay, and just take the half to the other, this 2 to the other side. So, all of these things will get a factor of half. So, this becomes minus 1 over 2, this becomes 1 half, this becomes 1/2, this cancels, this becomes -3/2. Okay. The key result, what is the link between B and M? Previously it was -1/2 log base 2 of M. Now it has become -3/2. So for every doubling of the input of the sampling rate, you are not going to get a half bit improvement, you are going to get 3/2 bit improvement. Okay. So that is a significant jump, because that tells me that, oh, actually we can now start to see a very significant advantage, and that is something that we can definitely leverage. Okay. So the additional term, the benefit that we get is that it is going to be 3/2. So every doubling of M will correspond to a improvement of 3/2 bits improvement, right. So it is as if you had 3/2 additional bits in terms of the quantization. So example, if I have M equal to 64, which is 4 times 4 times 4, what I should expect is that first multiplication, factor of 4 gives me 3 bits plus 3 bits plus 3 bits. Previously they were all contributing 1 1 1, now they are all contributing 3 3 3. That should be equal to 9 bits of improvement, correct. That is what you would get, except that if you go back and look at the equation a little bit more carefully, there is a term that was not there before, and that term is actually in M is reducing the number of bits needed, this term is actually increasing the number of bits needed. So basically go back and look at that 1/2 log base 2 pi squared by 3, that additional term, do not overlook that. The additional term is 1/2 of logarithm base 2 pi squared divided by 3, that comes out to approximately 0.86. So you gained 9 bits, you lost 0.86 bits. So effectively what you will get is approximately, if you take it as 0.9, effectively it is a 8.1 bit improvement, and you achieve this with a simple first order noise shaping. With a first order noise shaping of the type 1 minus Z inverse. Very simple. Of course then you say, okay, why not second order, why not third order, why not fourth order? Yes, yeah, that is what you should ask, that is the right question to ask. Okay, so let us do, everyone is okay with this? The improvement, but there is a scale factor that kind of pulls down the gain a little bit, but the net gain is still very, very substantial. So you achieved a very, very significant, I mean you can go from 8 bits to 16 bits just by increasing the sampling rate. Okay, so can we do second order noise shaping? I will leave this as an exercise for you to verify, but basically the structure is like this. You pass it through a C to D with oversampling, okay, oversampling, followed by the A to D conversion with the noise shaping. So the noise shaping now is going to be in the following form: plus sign 1 minus Z inverse, that is the first integrator. So if that gave you a first order transfer function, you expect that there should be a second integrator that will give you a second order transfer function, which is actually correct. There are two in series with the plus sign, with the error entering into the picture, and of course now you have to design the feedback taps correctly. The feedback taps are Z inverse, so that looks exactly like a first order, right. The latter part looks like a first order quantizer embedded inside a second order. So, basically you have embedded inside another feedback mechanism. So, effectively, so if you take this to be y of n and this to be x of n, like before, please go through the analysis and obtain the transfer function, and please verify that what you get is y of z is equal to x of z. Again, no change in the input signals component, plus e of z into 1 minus z inverse whole squared. So, which then says that my modified spectrum S e hat of E of j omega will be equal to sigma E squared, that is the white noise. Now, what is inside the bracket is 2 times sine omega by 2, previously it was a factor of 2, now it is raised to the power 4. Okay. So, just to give an intuitive feel, okay, in one case you saw sine squared omega by 2, in the other case you are going to see sine power 4. So, if this is sine squared omega by 2, then this is going to be sine power 4 because it is less than 1. So, it is going to rise much slower, but eventually will reach the same. So, this is sine power 4 omega by 2 all the way from 0 to pi. Okay. So, effectively what did you do to your noise? You pushed it out further. So, in the region of interest it was further reduced. So, if you were to draw the spectrum, if this is the input spectrum, the first order noise shaping pushed the noise out with a certain slope. Okay, you cannot remove the noise. All you have done is you have sort of distributed it in a non-uniform way. The uniform distribution would have been something like that. What you did was you did it in a non-uniform fashion and therefore it got pushed out. Okay, the second order noise shaping does it even further. So, effectively what you see within the signal portion of it is going to be advantageous for us. Okay. So, basically what is the portion of the noise that is going to affect you now is only this portion, which is substantially less than what we would have had to deal with if you had either gone with the no noise shaping or with the first order noise shaping, and this is where. Okay. Now, why not third order, fourth order, fifth order, just get this thing as flat as possible. Control theory people will tell you unstable, which means the region in which this thing will, there are certain inputs for which you may become unstable. So, up to second order we can guarantee stability. Once you go beyond second order, there are restrictions in terms of stability. So, you have to also keep in mind the issue of stability. So, n greater than 2, we need to keep you have to study the stability, and you also have to restrict your input signal to a shorter range. So, again what is the to study and ensure stability. Okay. So, we say that up to second order we can do the noise shaping with the guarantee of stability. So, then what people said was, if I still want to get higher order noise shaping, what will I do? I do second order noise shaping, and then on that I will do a second order noise shaping. So, basically shape noise, and basically you can do. So, basically it is a cascaded second order noise shaping which you can do, of course, and you can achieve the benefit of that. Okay. So, let me just sort of say that that is at least a initiating point for you to start thinking about some very interesting applications of multirate signal processing. Okay. Of course, there are many more applications. I had thought of at least 2 more applications, but given the time constraint, maybe I will just restrict myself to 1. Yes.
If you apply a second order noise shaping and then you do it again,
yeah,
your new x of z will be the original signal plus the error. So how does that help?
Say that again.
Like if you do a second order noise shaping first,
Correct.
your output signal will be your input signal
So
plus the error.
yeah, so the way you feed your the point at which you feed, where you take for the second order noise shaping is not at the output of the signal. So you will basically take the error and do shaping. So basically you keep working on the error signal. So the way you construct the higher order is not on the input signal itself, but on the error. So you take the difference, take the error, and then try to shape it even further. Okay, good. So let's very quickly look at just one more example. Supposing I have to design a high order FIR filter. Okay, again these are cases where you will encounter very often. So let me just give you a construct for you the scenario. The signal is a signal sampled at 1000 hertz, and you have been asked to design a low pass filter with a cutoff of 20 hertz. Cutoff of 20 hertz, that means pretty sharp cutoff. Okay, so omega c is equal to pi over 25. Pi over 25. Okay, and you are asked to design a filter with good stop band attenuation, 60 dB stop band attenuation, and you want to have a flat pass band in the range 0 to 20 hertz. So basically you want to have you can't just start drooping all the way from the omega equal to 0 hertz. So you want to have a flat pass band as much as possible. You want to have a good stop band attenuation, and this is a tough filter design problem. Okay, so you give these to your MATLAB filter design problem. It will say that the filter order typically will be n greater than 1500, and it will say out of memory, and it will return back saying I cannot design this filter. Okay, so here is the trick or multi-rate signal processing to the rescue. So you tell the program, well, don't worry about it, design something which is a little bit more easy for us to do. So this is 1000 hertz sampling frequency, half the sampling frequency is 500 hertz, and we say that okay, design a filter with a cutoff around 200 hertz, okay, with a reasonable flat pass band, and you do a cutoff over here. Okay, so this is around 200 hertz. 200 hertz. Okay, you design, you write down the specifications, and the algorithm does a calculation, and let us say that it came up with an estimate that it is 168, and basically you allowed a reasonable transition band. Okay, you didn't make it very tight. So it came up with a filter order equal to 168. But this is not the filter you want. What you want is a filter that will cut off at 20 hertz. You remember the IFIR technique? What did we do? We will upsample by a factor of 10, which means that it will compress the spectrum from 200 hertz, it will go to 20 hertz. Your pass band will become 10 times sharper, okay, the transition band. So effectively the strategy that we had was that you will design this filter H1 of Z, which is corresponding to this 168 tap, and then you would follow it up with a upsampling by a factor of 10, and then you would have another filter which will remove the images. When you upsample by a factor of 10, this is the one that removes the images, removes the unwanted images. Okay. Now this is the underlying technique that that we need to do, but here is a very clever way to do it, and I will leave you to sort of go through and make sure you are so first step, you've got your filter order is 168, filter length is 168, n is order, n plus 1 equal to n 168, the length is 168. Okay. So, so this is length. Take a 168 point DFT. Take 168 point DFT. What will that give you? It will give you the frequency response of the filter with values from 0 to 167. The last one will be 167 and 168 of course will map back to 0, okay, DFT coefficients. Okay. Now, this is the sampling frequency, that is 1000 hertz. Now, at what frequency will you get the 200 hertz cutoff? So, 500 hertz basically corresponds to 84, 168 by 2, that is 500 hertz. I will write the frequencies in orange, 500 hertz. So, 200 hertz will be approximately, you divide that by 2.5, it is somewhere around 33. So, your filter response will have these sorts of things up to 33, around 33, and then you expect to see something, some small values, right, you get to see some small values, that is your stop band. Agreed? This is what you would see. 168 points, you took a 168 point FFT, these are all the pass band. So, this corresponds to pass band, and the rest is the stop band. Okay. Now, what I want you to do is pay close attention to what we are doing. So, basically take these samples from 0 to 84, 0 to 80, take these samples, okay, take those 0 to 83, 0 to 83, okay, that is the 84 samples, 0 to 83, okay, and the last 84 to 167, 84 to 167, but leave a gap in between. And the gap that is in between is exactly 1680 minus 168, that is equal to 1512 samples. Okay. These 1512 samples are all the, I am going to set them to be equal to 0. Okay. Visually okay. What did I do? I took 200 hertz cutoff filter with a sampling rate of 100 hertz. I computed a filter of 168 taps, took the DFT. The DFT will have sort of mirror image symmetry, and I separated it out and inserted some number of zeros, and exactly so that I will now get this will become sample number 1680, this will become sample number 0. So, effectively what we see is these samples, and then towards the end you will see again these samples. Okay. Now, 33 by 1680 into 100 hertz is equal to what? 20 hertz. Right, exactly 1/10 of what it was before, because you now expanded it by a factor of 10, right, from 168 you went to 1680. So, which means that 33 if it corresponded to 200, the same 33 will now correspond to 20 hertz, 20 hertz. So, what you do is take the inverse DFT of this, but now it is not 168 point inverse DFT, it is a 1680 point inverse DFT, and what you will get is a 1680 tap filter with omega c corresponding to 20 hertz and satisfying all of the requirements, all the specifications. The stop band attenuation you already satisfied, right, you when you design the 168 tap you already specified it. So, effectively what is the trick involved? Previously what did we do? You upsampled in the time domain, you inserted 9 zeros and then you passed it through a filter, correct? Okay. In the frequency domain, what was it going to do? It was going to have these 10 copies of the signal, and this low pass filter would remove those unwanted symbols. What did you do here? You didn't even allow those copies to come in. It's the same as saying the copies came in when I inserted the zeros, but I interpolated with the ideal low pass filter. There is no trace of any small bump or anything, everything is 0, perfectly 0. So which means that this is effectively like interpolating with an ideal filter. If I did an ideal filter, that is what I will get, and it didn't cost you anything. Basically it was one inverse DFT and designed, and you incorporated 2 techniques that we have learnt. One is the interpolated FIR technique. The second one is using the FFT to your advantage, so that you do not have to actually do the physical interpolation. It sort of comes out as a inherent advantage into the system. Okay, so this is a starting point for us to start saying, the whole toolkit of multi-rate signal processing has got a very rich ways of helping us in all of our designs. So you always try to see, okay, upsampling will compress the spectrum, I can exploit that, downsampling will go this way. So you kind of always keep looking at ways in which you can exploit the techniques that you have learned to your advantage. Okay, so in a nutshell, what the course is all about is to say that the signal processing is built on a foundation where you have a fixed sampling rate. To that toolbox, you add the flexibility to change the sampling rate, input, output, and what are the implications when you downsample, what are the implications when you upsample, when you insert zeros, what is. So once you have this additional toolbox, then you start to see that, oh, okay, in communications, for this application I need a filter. Here is an advantage, I can take advantage of it. If I didn't have this notion of multi-rate signal processing, I would at this point give up and say, well, 1500 tap filter I cannot design, right? And or you would have to go through some extremely complicated process to design it. But whereas this one says, hey, I can design it through a 2-step process, which will sort of almost trivial, and will give you the advantage that we are looking for. Okay, thank you very much. That's the end of the course, and we very thank you for the way in which you have participated, and wish you all the very best.